I want to describe to you one such way, which gets at them really in a much more kind of geometric way. Not in every field theory, but in a pretty big class of field theories. So here the big tool was line defects, and in this next approach, the key tool is going to be surface defects. But again, the sort of overarching principle is that if you want to study a field theory, you better study its whole spectrum of defects all at once. Okay. So today, BPS spectra of, BPS spectra via surface defects, supersymmetric surface defects. And this strategy that I'm going to describe actually should be a pretty general strategy. It should work essentially in any theory that has surface defects. But to be concrete, and because this is the case that's really been worked out, I'll describe it in the so-called theories of class S. And here, unlike in the previous day, yesterday I tried to tell you more or less the complete arguments. And today I'm going to give you kind of sketches of the arguments. But the arguments are going to be actually quite parallel to what we did in the previous, previous talks. Okay, so now let me say a word about what the answer is going to be. What I want to say is that the answer will look like something that would come from string theory. So it's going to involve ultimately some networks of strings. But what I want to emphasize about it is that it is not, it looks like something that comes from string theory, but in fact it is not coming from string theory here. So we're deriving it from sort of purely gauge theory assumptions. It's derived sort of purely within gauge theory, with, granted, a few, it's derived within gauge theory with a few assumptions about the gauge theory, and you can argue about whether those assumptions are exactly proved or whether they're just good guesses. But in any case, it's something that doesn't use string theory, but yet you kind of discover the string theory from oddly enough, starting from just the field theory. So we'll see how that goes. So what are the players in this story? So what are the theories of class S? So this is a construction that's been sort of broadly exploited over the last couple of years. So you start with, the main thing that you start with is a Riemann surface. So let me call it C. Maybe here's my Riemann surface. I'll take a number, k, which is greater than or equal to 2. And that's going to be, so the way you get these theories of class S, for those who know, is you start with some 6-dimensional field theory, you compactify it on this Riemann surface and get a 4-dimensional field theory. So the 6-dimensional theory is sort of almost unique. There's almost only one, but not quite. I mean, there's one for every possible gauge group, for every ADE, actually not even gauge group, for every ADE algebra. And so I got to pick which ADE algebra I'm going to do, and the one I'll do will just be A k minus 1. And so I fix an integer k just to tell me which of those groups I'm going to do. Then, in addition, you don't absolutely have to, but you frequently consider this Riemann surface to have some defects on it, so some marked points. So let me call them ZL. L goes from 1 up to, say, n. And then associated with these marked points, there's some parameters. There's some continuous parameters and some discrete parameters. Just to fix your ideas, just to get some idea of what kind of parameters they might be, sort of one typical choice for these defects is to have them labeled just by a bunch of complex numbers. So basically k complex numbers for each defect. So the idea is that if you give yourself this data, or slightly more general sort of defect data, for those who have thought about this construction before. Fortunately, this defect data won't play too much role in what we're gonna do. So the claim is that if you have all this stuff, so basically just a curve with some marked points on it, then you get an n equals 2 supersymmetric quantum field theory in 4 dimensions. So this is, in a sense, this construction really goes back to Witten. We used it, and Gaiotto made a number of very important observations about this theory, which led to then these theories then got connected to the AGT correspondence. Well, AGT was discovered as a statement about these theories, and so for that reason, these theories have been sort of much explored lately. So, particularly, all of the data of the theory is somehow geometric from the start, and so all the answers to every question about the theory should also be kind of geometric. They should be answered in terms of somehow this Riemann surface. And so if I want to understand what the BPS states are, ultimately they should be something that's just made out of this Riemann surface. So that's what I'm going to tell you, is how to make the BPS states out of this Riemann surface. So, okay, fine. Well, in order to do that, so the BPS states, first of all, as we've been emphasizing, what the BPS states are may depend on exactly where you are on the Coulomb branch of this theory. So I have to tell you, well, what is the Coulomb branch of this theory? Okay, well, the Coulomb branch is also something geometric. So what's a point of the Coulomb branch? A point of the Coulomb branch of these theories of class S is specified by, this at first will look sort of unintelligible, and then we explain it. So it's a tuple of a bunch of things, phi 2 up to phi k. What are the things? Well, each phi r is a meromorphic R differential on the curve. What does that mean? What it means is, let's just think of writing this thing in local coordinates. So what's phi r? So it's some kind of function on the curve. It's something that depends on the parameter z, the coordinate on the curve. But it's not globally a function. What it globally is an R differential, meaning the thing that's really globally defined is fr of z dz to the r. So said otherwise, it's a bunch of functions, but when you transform coordinates, you need to include the rth power of the derivative of the change of coordinates map. Okay, so we've got a bunch of those things, phi 2 up to phi k, a 2 differential up to a k differential. And they're meromorphic, so they have poles. They're meromorphic and they have poles exactly at these defects. And the residues of those poles are controlled by, they're determined in some simple way by these numbers, MLI. So suppose I have all that stuff. I give myself a meromorphic differential on the curve for each index from 2 up to k. Then that's supposed to be the data that determines for me a point of the Coulomb branch. All right, so well, in a moment I'll write an example of this, which might make it slightly more intelligible. But first, let me say one more thing, okay, which also might help. So what we're used to thinking about, those who've thought about n equals 2 theories before, yeah.
You hold that before the parameters and A starting from 1 to k, and
yeah.
below you hold with 5.
Yeah.
From 2 to k. So
yes.
with A equal to 1, what I do?
Sorry, with k equals to 1?
A equal to 1.
What's A? Where's it? I don't see an A here. I. Ah. Oh, well, yeah, so, I mean, here I've got, okay, great. So, yeah, what's the relation between, so I said it's controlled, but you want to know exactly how is it controlled. So I guess there's one thing more about these parameters, which is that their sum should be 0. Sum I equals 1 to k. And then the idea is that, yeah, how does it go? So the residue of phi r is going to be the rth elementary symmetric polynomial in these m's. So I mean, it's not that the residue is just equal to the m's. There's some formula that relates them. I can work out the precise formula, but maybe I'll do it. Maybe I should do it later because it won't be strictly needed for what I'm about to say. So So okay, so given these differentials, I'm supposed to have a point of the Coulomb branch. Well, the way we're used to thinking, most of us are used to thinking about the Coulomb branch of an n=2 theory is in terms of this auxiliary curve, which is called the CyberWitten curve. So how do I see the CyberWitten curve in this thing? It is not this curve that we called C. Rather, what it is it's a covering of C that's given by this equation. So it's governed by the CyberWitten curve, which is given by this equation, sigma. So it's all points lambda and z in the cotangent bundle to C. So what does this mean? So think of z as just a point of the curve and lambda as a cotangent vector. Obeying this equation, lambda to the k plus the sum from r=2 to k, lambda to the k minus r phi r = 0. Okay, does that help? So here's our curve C. And then we have this equation, which is a kth order polynomial equation, and so we have some k-fold covering of C. For every point of C, this equation has k solutions, and so we have some k-fold covering of the curve. And this thing is the CyberWitten curve, and so it also has the corresponding CyberWitten differential. CyberWitten differential. Which is just given by this sort of tautological Liouville one form, but just lambda itself. So okay, so from this curve that you use to define the theory, you construct the CyberWitten curve. The CyberWitten curve depends on these phi r's. So every choice of these phi's gives me a different CyberWitten curve. In other words, a different point of the Coulomb branch. So for example, to be really concrete, let's see how you recover some sort of known field theory in this language. Let's take the theory, just our favorite example. So n=2 super Yang-Mills with gauge group SU2. So in that case, I'm going to take the A1 theory. In other words, I'm going to take this parameter k to be 2. And so then I was supposed to give a whole bunch of differentials, phi2 up to phi k, but in this case, I just give a phi2. And what these phi2s will look like, so my curve will be CP1 with two defects, one at the North Pole and one at the South Pole. And so my differentials are going to be just some quadratic differentials on CP1 with poles at 0 and infinity. And explicitly what they are, here's the formula for them. So this has dz squared, so it's a quadratic differential. It has this parameter lambda, which is just the QCD scale of the theory. And then it depends on one more parameter, which is u. So as I vary the parameter u, I'm moving, in the Coulomb branch, I'm moving this, which is equivalent to just moving this quadratic differential. And so the corresponding CyberWitten curve now, what is this equation that I wrote? Well, in this case, the equation is just lambda 2 plus phi2 of z equals 0. And if I want to write that a little more explicitly, I might even represent lambda. If I represent lambda as y dz, then the equation becomes y squared plus lambda over z cubed plus u over z squared plus lambda over z equals 0. So you know, if you want a sort of concrete formula for the CyberWitten curve, here it is, but it comes out of this kind of general recipe. So for any theory of class S, there's this sort of standard recipe for building the CyberWitten curve as just a k-fold covering over the curve C. So here, this particular one is just a 2-to-1 covering over the curve CP1 parameterized by Z. Okay. So far I told you just if you have a curve, you get a corresponding field theory. Now, we want to study the BPS states, and we want to study them by the same kind of technology we used before. That means, first of all, line defects, and second of all, surface defects. So where are the line defects and surface defects in this story? That turns out to be something else that's quite pretty. So a closed path. So first of all, what is a line defect? So that turns out to be represented by a closed path on C. So I have my curve C. It has these defects on it. And now, suppose I put some closed path on there up to homotopy. It turns out that for every such path, there's a corresponding supersymmetric line operator. So this was the observation originally of Drucker, Morrison, and Okuda. It's kind of a cool thing. Like, for example, for this SU2, the pure SU2 theory, n equals 2 super Yang-Mills, you could ask, where's the Wilson loop? Well, the Wilson loop is just the loop that goes around the equator, separating those two marked points.
P is defined on C or on C with marked point?
Oh, thanks. Yeah, on C, right. On C minus the defects, yeah. So that's right. It's up to homotopy, but homotopy, of course, is not allowed to cross the defects. And there's some more elaborate thing. For some of the defects, you can have paths that go into the defect. That's how you get the 't Hooft operators in this theory. Let me not get into that. But generally, roughly speaking, it's just a path on the curve. OK, great. So that corresponds to, if I would represent what this thing looks like in space-time, well, factoring out the time, in space, it just looks like a point. Just those line defects that we were representing in the last talk, just a big, heavy blob. OK. So these are line operators, line defects. But now there's something else. So how about, suppose we consider just a point, some arbitrary point on the curve. Not one of the defects. The curve has defects in it which are fixed for all time. But suppose we also just mark another point. Well, as it turns out, that corresponds actually to a surface defect in the theory. The kind of underlying reason for this is that in 6 dimensions, the 6-dimensional theory has surface defects in it. And so those defects, if you dimensionally reduce them in different ways, can give rise to defects of different sorts in the 4-dimensional theory. So if you put it on a curve in C, then you have 1 dimension left over and you get a line defect. If you put it on a point in C, then you have 2 dimensions left over and you get a surface defect. So the surface defect, if I factor out the time, it looks like kind of a line. So it's like a string sitting in space. Let me call that defect SZ. And then there's yet another thing you can do, which is, suppose we now study a path which goes between 2 of these points. So instead of a closed path, we study an open path. So I've got 2 of these defects. So this was at the point Z, and I got a surface defect. But the surface defect depends on, the surface defect has continuous modulus. The Z can move around. So here now I have a path from Z1 to Z2, an open path. And so what does that correspond to? Well, if you think about it, there's sort of only one sort of plausible guess for what it corresponds to. What it corresponds to is a kind of supersymmetric interface. So, or like a domain wall from the point of view of this surface defect. So I've got one surface defect, say SZ1, a second surface defect, SZ2, those corresponding to those 2 points. And then I have a supersymmetric interface between them, which is represented by this open path. So think of it as a kind of line defect. It's a line defect, but it's a line defect which can't live just in empty space. It has to live on the interface between these 2 surface defects. So that's a sort of geometrically natural thing. I guess I should also say that as in the last talk, the line defects always depend on a choice of phase. They're supersymmetric with respect to a particular phase. The surface defects are not like that, but these interfaces are, of course, also like that. So with a path together with a choice of phase, gives me a sort of supersymmetric interface with a particular phase. So it sort of looks like a very heavy BPS particle, but now it's a BPS particle sort of in the theory that lives on the surface defect. Yeah. Yeah, I mean, well, I comment on their origin in the 6-dimensional 2,0 theory, where they all come from the surface defect in 6 dimensions. Now, well, okay, so now if you ask where does that surface defect, if you're not satisfied with some statement about the 2,0 theory, but if you want to know where that comes from in 11-dimensional M theory, then the answer is yes, it comes from M2 branes ending on them. But all of these objects come from the same thing. They come from this M2 brane ending on it, just sort of arranged in different ways in the 6 dimensions. Yeah. They're different, exactly. So in 6 dimensions, you just had this one thing, which was a 2-dimensional defect. That was the end of the story. But now I take that 2-dimensional defect and I put it this way, I put it that way in the splitting of the curve times R4, and I can get various different things. Anyway, however you get it, this is the dictionary of these supersymmetric defects. And now in this setting, so in this setting we can consider now various kinds of BPS states. So what are the various kinds of BPS states that we have in this theory of class S? Well, so in particular, so first we could have the usual 4-dimensional sort of bulk BPS states that were the main object of our study last time. So those are just the regular 4D BPS states. Okay, so their charges. Yesterday I just had this charge lattice gamma, which was the sort of abstract lattice of electromagnetic charges. Now, in this world, it has to be geometric. Everything's geometric, and actually it's quite simple to say what it is. What it is, so we had this curve C, and we had its covering, which was some Riemann surface, some covering surface sigma. And the charges of BPS states are nothing but the closed loops on sigma. So elements in the homology of, in the first homology of sigma. Okay. And so those are counted by, as we said last time, they're counted by omega of gamma. Okay, great. And now we could have the same thing as we talked about last time. We could have these frame BPS states. Let me not write those separately. So sorry, this is the first homology of sigma with integer coefficients. Okay, but now we can have something new because we have this surface defect in the story. Because we have this surface defect in the story, we can consider BPS states which just live in the theory on the surface defect. So BPS states which are constrained to lie on the defect. So think of them as being sort of, beads which are attached to this string. And they also carry a charge, but the charge that they carry is a little bit subtler. So the charges that they carry turn out to be represented by, maybe it's not so surprising, they turn out to be represented by, so here's my surface defect Z. Here's my surface defect Z. Now the various points lying above Z, have the interpretation as the different vacua of this surface defect. So I didn't tell you everything I should have told you about this surface defect. So one property of this surface defect is that it's actually completely massive in the infrared. So it has no propagating degrees of freedom on it, and it just has a finite set of supersymmetric vacua. Those vacua correspond one-to-one to the sheets of the CyberWitten curve. And in particular, now, if you have a BPS state which lives on the defect, what's the classic kind of BPS state in a 2-dimensional theory with n equals 2, 2 supersymmetry, which is what this has? The sort of classic thing that you think about is the Landau-Ginzburg soliton that interpolates between one vacuum and another. The way that gets encoded in this picture is that the charge of this soliton, the charge of this BPS state, is represented by a path which interpolates from one vacuum to another. So it's like a soliton, but it has a little bit more information than a soliton. It doesn't only keep track of just the two vacua, but it keeps track of a path that goes between them. That's what extra you get by taking this 2D theory and coupling it to four-dimensional physics. Okay, so anyway, the geometric picture is just this. So the charge is now represented by an open path. And then there's even another thing you can do. So you can also count these. So there's some count. I called the charge A, so the count you would call mu of A. And then there's even a third thing, which is the analog of those frame BPS states that we had. So suppose now that I have two surface defects, two distinct surface defects, and I have a path going from one to the other. So here's Z1, Z2. I fix a path going from one to the other. Now, I told you that that path corresponds to a sort of supersymmetric interface, which is like a line defect that's fixed to live on the boundary between these two surface defects. So now, just like we had for the usual line operators, we can ask now for the supersymmetric ground states of this system, a kind of complicated system that's made in the UV of these two line operators and an interface that connects them. The supersymmetric ground states of this system are a kind of analog of the frame BPS states. So I call them sort of 2D framed BPS states. So they're BPS states now of this interface. I'll draw them like that. And their charges, perhaps not surprisingly, their charges correspond to paths which go from some free image of Z1, so some vacuum of the line defect of the surface defect over here, to some vacuum of the surface defect over here. So, one possible charge for the thing would be like this. Okay. Okay. So those are the kind of players in our story. So these are kind of framed BPS objects, and so they're also counted by a frame BPS index, which depends, as usual, on the charge. So I want to count all states with this particular charge, and they're states of a particular surface, particular interface represented by the path P, and they depend potentially on the phase of that interface, which is the parameter theta. Okay, so we have a lot of parameters here, but the geometry is pretty simple. The geometry is just ultimately the geometry of paths on this CyberWitten curve, open and closed paths. Those have a physical interpretation in terms of these various different kinds of BPS states. Okay. All right. Yeah.
What does angle theta?
So as usual, so the angle theta is the one thing that doesn't have a sort of direct geometric meaning only on the curve. That's something extra. I mean, you can understand it. Well, yeah. Let me not try to say so. So that single parameter. We will say it play a geometric role by the end of the talk, but so far it's not clearly represented here. That's right. So that's just an extra choice that you make. Okay. So now let's ask the same question as we asked yesterday, which is how to compute the BPS spectra. And it turns out that just like before, the easiest, in the last talk I got a lot of mileage by sort of first studying the frame BPS states, which sound like the most complicated thing. And here too, the best thing is to study the most complicated thing first, which is these frame 2D BPS states, these things that are attached to open paths on the surface. So you actually start, strange as it sounds, you actually start with these sort of complicated things. And so you ask yourself the same question that we asked last time, namely, first you don't try to calculate them, but you just try to determine what their wall crossing is going to be. And you use essentially the same kind of ideas from the last talk. But now for this sort of coupled 2D, 4D system. And so if you like, there are various different kinds of wall crossing now that you have to think about. So you remember the usual story was that if I have one of these framed states, one of these heavy framed BPS states, it can decay by emitting one of the usual kind of BPS states. That was the link between the framed states and the usual states. Now in this context, it's a similar thing, except that there's sort of there's two different kind of decay channels. So one is that my frame BPS state could decay by emitting. It could decay by emitting a. Gosh, it takes a while to draw this thing. It could decay by emitting an ordinary BPS, an ordinary four-dimensional BPS state. In other words, I start with this guy and it emits a guy of charge gamma into the bulk. So this corresponds to, you have an open path, and then you change that open path by adding a multiple of a closed path to it. And the other thing that could happen is something that was familiar in the theory of two-dimensional wall crossing, studied by Chakotay and Vafa a long time ago. More or less studied by Chakotay and Vafa a long time ago, which is that you could decay by emitting a two-dimensional BPS state. So it could decay by emitting something. Sorry, that should have been like that. It could decay by emitting something, one of the two-dimensional solitons, just along the surface of the defect. But for each of these kinds of wall crossing, you can prove a kind of wall crossing formula by just exactly the same methods that I described last time. And just using those methods. So just use the methods from last time for this more complicated wall crossing setup. So just using those methods plus actually two more principles. So one of them is that if I have two defects that are very widely separated, so imagine that I have defect 1 and defect 2, and I spread them way out along the line. And so I have three kinds of surface defect that can be separated by two interfaces. That the Hilbert space of ground states of this should be just this, if I separate them far enough, it should be just the ground states of one tensor with the ground states of the other. So this should be just equal to the BPS states of the first one tensor the BPS states of the second one. So this is going from Z1 to Z2. This is going from Z2 to Z3. So we have here this LP1 and this kind of LP2. So this says, if you like, if you look at the geometry of the curve, what it says is that you can take a long path and sort of cut it into shorter paths. And then the last principle that you have to use is that if you have the trivial interface just corresponding to the trivial path that goes from a defect to itself, that this is just equal to the ground states of the surface defect itself, just the ground states of SZ. So you use just using the same kind of wall crossing methods we used before, plus these two principles, we get a result. And what is the result? So what do we conclude? From this, you're actually able to completely determine all of the frame BPS states. Morally, because now imagine what this says. It says that if I have an interface, if I have the trivial interface corresponding to a path of sort of 0 length, I know exactly what its BPS states are. And so now all I have to do is start with that interface and then move one of the surface defects away to trace out a longer and longer path. Every time I cross a wall, but I know exactly where the walls are, every time I cross a wall, I'll get some new BPS states of some known, with some known wall crossing formula. And so I can determine all the BPS states just from these kind of simple wall crossing ideas. And what's remarkable is the answer is pretty simple. The answer is something you can actually digest. So now I'm just going to tell you what the answer is. Or rather, I'm going to tell you sort of the key geometric ingredient in the answer. So now we can determine all frame BPS degeneracies. So what is the answer? Well, the answer is given in terms of a sort of new geometric gadget. Which we call a spectral network on the curve C. So it's going to be some network of curves on C depending on the point of the Coulomb branch. So it depends where you are in the Coulomb branch, and it depends on this phase theta. And that's all it depends on. So what I want to do now is tell you what this spectral network is and sort of roughly how it determines the BPS degeneracies. So sorry, when did I start? 25 minutes. Okay. Okay. So let's begin with the special case of k equals 2. So this is the case of compactification of the A1 superconformal field theory in 6 dimensions. This would be enough to get the SU2 theory in 4 dimensions, but not to get the higher groups. But let's start with this one. So in that case, so what is our data? Our data in this case is just we have a curve C, and we have just a meromorphic quadratic differential, which I called phi 2 on C. That's all, nothing else. So that's enough to determine where we are on the Coulomb branch. It's just this meromorphic quadratic differential. And let's assume that this meromorphic quadratic differential has only simple zeros. What that means is that we're not at a singular point of the Coulomb branch. When this thing develops double zeros is exactly when you have some singularity. So let's assume that we're not at such a place. And now, so we're given this phase theta. That's going to be the phase governing, the interfaces that we're studying. And so let me make a definition. I'll define theta trajectories. So what's a theta trajectory? So theta trajectories of phi 2. Well, what are they? So there'll be paths on the curve C, but not just any paths. There'll be paths on C along which, so we have this quadratic differential phi 2. If I take its square root, I get just a 1 form. Now let me take that 1 form and multiply it by e to the minus I theta. Okay, so that's another 1 form. It's generally complex because phi 2 was a complex object. I take a square root, I get something else complex, but there will be directions along which it's real. And so in fact, these trajectories, if you sit at any point, you can always find a direction in which this square root of phi 2 is real. If you think of square root of phi 2 as being dz, the direction in which it's real is just the direction dx. So at every point, there's some direction in which the thing is real. And so these trajectories, they make up a foliation of this curve C. And what does this foliation look like? Well, so if you sit at a generic point of C, you just see some foliation of trajectories like this. There's 2 places where something special happens. So let's call this foliation f of phi 2 and theta. So f of phi 2 and theta has singularities. It's singular at the defects. And if you look at what happens around the defects, what happens is that these trajectories kind of spiral in. And at the zeros of this phi 2. So phi 2 was this quadratic differential. It has some zeros. And at the zeros, what you have is this kind of three-pronged singularity. In fact, let me designate that like this. So the trajectory is kind of, the trajectories have this kind of three-pronged singularity here. OK. So now here's what we're going to do. We're going to look just at the trajectories. We're going to focus on these three critical trajectories. These three critical trajectories that emerge from each zero. And this, so I told you I was going to define some complicated thing, which I called spectral network, but actually in this case it's pretty simple. It's just the union of all these trajectories. So what does it look like? If I would try to make a sort of global picture of it, well, I've got a bunch of zeros of my quadratic differential, and then I've got a bunch of defects, which are like poles. And what generally happens with these trajectories is that they come out of they're born at the zeros, and eventually they run into the poles. So you'll have some kind of picture like this. And then this one maybe goes here. This one goes down here. They never cross, so in principle I should like thread it in there. Yeah, OK. Maybe I won't draw that spiraling from now on. Oh no. Yeah, I'll show you maybe computer pictures later. So you get a picture like this. So you get some kind of totally combinatorial gadget, which is just you have a bunch of marks on your curve and these trajectories. Now, what is the physics of this picture? So the physics of this picture is that these trajectories are the points of, they are the walls of marginal stability for the frame BPS states. So if we picture having one of these paths now. So remember, to every open path, there's some BPS spectrum attached, the spectrum of frame BPS states. And the statement is that that spectrum jumps exactly when one of the endpoints of the path crosses this network. So I didn't tell you how I derived this, but it was derived, I swear, just by the same kind of stuff we did last time. So you can find out exactly where the walls of marginal stability are. And then, so moreover, what that means is, so I guess I should write that. So W of theta phi 2 is the locus of marginal stability for these quantities, these framed 2D, 4D BPS state counts, so kind of tricky gadget, omega of A, and dependent on, like this LP theta. And so in particular, if you want to actually know the BPS spectrum now of these frame BPS states, all you have to do is, there's some algorithm where you take your path, you look at all the places where it crosses this picture, and you make some simple computation. It turns out what you actually explicitly do is you have to multiply together a bunch of matrices, one matrix for each path that the thing crosses. So what happens? So the framed BPS counts, so sorry. These things are determined completely by the intersections between the path P and this network. OK, fine. But our original interest wasn't in those, right? Our original interest was in the actual, honest-to-God, 4D BPS states of the theory. What do those have to do with these? So far, I only told you how to get these complicated frame things that involve surface defects. How am I going to get the more general ones? Well, that comes from the following strange phenomenon. So now let me show you a picture of one of these networks. So suppose we actually went and tried to study these networks. What would we see? So here's the simplest such picture that's interesting. So I've drawn kind of, think of this as being a region in a bigger curve. So I've studied quadratic differential, which has two zeros kind of close to each other. And so I'm shooting out these three trajectories from each zero. And now, so the frame BPS degeneracies are controlled by intersection of paths with these things. Now, as I change the phase theta, you watch what happens to this picture. So as you change the phase theta, this thing just deforms itself continuously, no surprises, everything is kind of smooth. And then suddenly something is going to happen. So right here, if you see, there's sort of two lines going to the southeast and two lines going to the northwest. And so a little path that crosses those would have a bunch of BPS states corresponding to both of those crossings. Now, a second later, okay, right here is the last moment, bang. Suddenly something changed, right? The topology of this picture suddenly changed. What does that mean from the point of view of the 2D, 4D BPS states? If I have a little path that crosses one of those places where the thing suddenly jumped, the frame BPS states, it seems, have suddenly jumped. Why did the frame BPS states suddenly jump? What's the interpretation of that? Well, if you look at what the jump is, you understand what the interpretation is. It's exactly the second kind of wall crossing that I told you. It's the kind of wall crossing where the 2D BPS states decay by emitting a 4D BPS state. So in other words, the four-dimensional BPS states, you can read them off by looking at the moments when this picture jumps in topology. So they're determined by the walls of marginal stability of the 2D theory, but in a funny way. They're determined by the moments when those walls of marginal stability jump. Okay. Let's see. Maybe I'll show you one more picture, a sort of slightly more interesting one. So, here's something a little more intricate, where as we vary the parameter theta, we're going to see three different BPS states. And by the way, the moment when the jump appears is exactly the phase of the BPS state. So there's one BPS state. Here comes another one. And then, here comes the third one. So that's a kind of geometric realization of a thing with three BPS states. Now, if you vary the parameters a little bit, in the same quantum field theory, this is actually one of the Argyres-Douglas quantum field theories. If you vary the parameters a little bit just by moving that middle branch point down, here we're going to see only two BPS states. So this is a kind of geometric realization of the wall crossing phenomenon, just as some very concrete thing about some differential equations that you have to solve. Here you find two BPS states, in the other place you saw three. That's exactly this simple wall crossing that I first showed you yesterday. Okay, so let me write. So what's the sort of moral here? So when you vary this parameter theta, this W can jump. When it jumps, these omegas also jump. And the interpretation is that these BPS states are decaying or forming by emitting or capturing 4D BPS states. So jumps of this network of marginal stability lines equals 4D BPS states. And so you can make this pretty precise. And so in the pictures that I just showed you, the moment when the BPS when the network jumps was associated with something special happening. It was associated with a trajectory that went from one branch point right into the other one, from 1, 0 right into the other one. That's what happens right at the moment when the picture jumps. And this one, so you can calculate exactly what the jump is, and it corresponds to a 4D BPS state, but moreover with degeneracy 1. And so this corresponds to a hypermultiplet. The other picture, there's another thing that can happen, which I haven't shown you yet, but I will show you, is that you can have a sort of closed loop that actually comes back to the original place. That corresponds to omega of gamma equals -2, vector multiplet. And in these theories, nothing else happens. You always get either hypermultiplets or vector multiplets, nothing else. And this picture, by the way, I should say, this picture, we didn't invent this picture. So this sort of geometric picture of what the BPS states look like in this kind of theories is essentially what was done by, Clem, Lerche, Meyer, Baffa, Warner. They derived it from a different point of view. So here we've sort of re-derived that thing, but we've derived it from this wall crossing of 2D, 4D BPS states. So this is a kind of geometric picture of what a BPS state actually is. Let me show you. I'll go into higher K in just a second. That's the really new thing. But let me show you the pictures in the SU2 theory. So here's the SU2 theory at strong coupling. So here it's most natural to draw it on a cylinder, and you have just two branch points. And so you look at, again, when does this picture suddenly jump in topology? And here you'll see it happen. You'll see it happen there. And then again, you should see it happen one more time with a curve going around the other side of the cylinder. Let's see. Right, yeah, there. So that's two BPS states, and that corresponds to the, in the strong coupling region of the SU2 theory, remember there were supposed to be these two, this monopole and a diode. So then you could ask, well, what the heck? In the other region, I was supposed to see an infinite set of BPS states. How is that going to happen? Well, the trajectories can wind more and more times around the cylinder. So in a different region of parameter space, you just see this thing. So did you see it? So there were infinitely many. Well, OK. I have pictures where I zoom in on that, but maybe I won't bother. So now what have I got? Like 3 minutes or something? 10. OK. So 7. So OK. So now I want to tell you. That's the study of these things. As it turns out, though, we didn't know this when we started, but it turns out that this is a very richly studied mathematical area. These what they call saddle connections and closed loops. Mathematicians have studied these things quite a bit, and they have results on things like, for example, the asymptotics of the number of BPS states as you, well, what we would call the asymptotics of the number of BPS states as you go to larger and larger charge. Things that should have a nice physical interpretation. In fact, I don't know their interpretation. Yeah, so they say, for example, that if you study just a closed compact surface, the number of these BPS states with mass less than a given m goes quadratically with m, and there's a definite coefficient for the asymptotic of that growth. There should be some simple physics interpretation of that, which would be quite beautiful to find. I don't know what the interpretation is. But anyway, that's a reasonably well-studied thing. But of course, the strategy as I described it, was not really limited to k equals 2. For any k, I could try to draw the pattern of walls of marginal stability and then watch how it varies as I change this phase parameter. So let me tell you what's the answer. What's the answer for the higher k theories? So here I have to be a little quick. So I want to really tell you the answer, so I have to give a little bit of notation. So let's label the sheets of this covering now by I going from 1 up to k. So remember, the CyberWitten curve is like this k to 1 covering over the base curve C. So then on sigma, we have the CyberWitten differential. That gives me k locally defined 1 forms, just taking the CyberWitten differential on each sheet. That gives me k1 forms that I'll call lambda I. And now, the analog of the trajectories that I had before, I'll define an ij trajectory with phase theta to be a path along which e to the I theta lambda I minus lambda j is positive. Is real and positive. So before I had the square root of phi 2. In that case, the equation was just lambda squared equals phi 2. So all the lambda there were only 2 lambdas, and they were both equal to the square root up to a sign. Now I have a bunch of lambdas, and so I define this more general thing called an ij trajectory. And now I look at all the places, all of the branch points of the covering. So I have this covering sigma over c. It has some branch points, and at each branch point is a place where 2 of the sheets are coming together. So a branch point of type ij. From the point of view of the 2-dimensional theory, these are places where some soliton, some BPS soliton on the defect would be becoming massless. So there's some distinguished special points, and from those distinguished special points, we're going to have these walls of marginal stability emanating. So the picture is like this. From each branch point, I'll do more or less the same thing as I did before. I'm going to shoot out 3 trajectories. And 2 of them will be ij, and 1 of them will be ji.